Hello everyone! In this video I want to present my Google Summer of Code 2019 project called Zen on Beagleboard-x15. Beagleboard-x15 is the embedded platform with 32-bit ARM processor of AMAP5 family from Texas Instruments. It also provides users with virtualization extensions. Zen is a hypervisor, which means that it makes possible for several operating systems to run simultaneously on one processor. Thus, the idea behind this project is to make virtualization more available for embedded developers. You might be wondering, if the board system on a chip supports virtualization extensions, what was the problem with running Zen on it, especially since AMAP5 family is supported by Zen? The main problem with that system on a chip was its interrupt controller. In a typical case, a modern ARM processor has one interrupt controller, General Interrupt Controller or GIC. And Zen hypervisor does support it, and it assumes that this is the only interrupt controller in the system. Beagleboard-x15 also has General Interrupt Controller, but it also has another device marked as an interrupt controller, Crossbar. Crossbar is the device responsible for remapping external interrupts to GIC lines. And since Zen knows only how to deal with one interrupt controller in the system, Crossbar Interrupt Controller made it impossible to run Zen without its modifications. The similar problem was with NVIDIA Tegra devices and their legacy interrupt controller. There were at least two possible approaches to solve the problem. The first approach was to hide the Crossbar Interrupt Controller and map some of the interrupts directly to General Interrupt Controller. The main flaw of this approach is that due to a small number of interrupt lines in the system on a chip's interrupt controller, 159 for external interrupts in the AMAP AM5728, only a subset of external interrupts can be made available to virtual machines. The second approach was to add support of secondary interrupt controllers, like it was done in Apache adding support of Tegra devices, and allow zero-domain virtual machines to configure them. And this approach was used in the project. As a result, we have a solution that adds virtualization support into Beagleboard-x15. So let's see how it works. First of all, we are booting into U-boot bootloader, and then we have to set up our IP address and host machine's IP address. And after that, we can boot images from our host machine. The next step is to set up some values in the device tree. For example, we describe a frequency of a processor. And now we can boot, and we boot Zen right now, and you can see that there are some writes into Crossbar register, and we are booting Zen, and now we are booting Linux. As you can see, Linux tries to access some of the Crossbar registers, and we are booting. It takes quite a long time, and you can see some Zen notices that there are some accesses to the Crossbar register that we have unmapped, and put some handlers on that region of memory. And now we are in Linux's console. We can switch to Zen, and for example we can dump zero-domain machine registers, and we can switch back to Linux and let's taste it. We can see our network interfaces. We can try to ping our host machine. It's unsuccessful because the network is not set up yet. So we have to set it up. So we are setting up an address for one of our network interfaces. And we make it alive, setting it up. So we can try to see the information about this network interface. And you can see that it is up. And now we can ping our host machine. Let's try to do it. And it's done. So it's working. And what I want to say is that though it's on the initial phase of Beagleboard-x15 support with them, and there are a lot of things to do, for example, testing zero domain and testing and implementing user domain, but the initial prototype, initial step was already done. I want to thank all the mentors from Zen side and also from Beagleboard.org organization, and I also want to thank Google for making this project possible. Thank you.